The solar system already existed. We can see it. We can measure it. We can predict where every planet will be years from now with remarkable precision. Yet, for decades, one problem refused to go away. Scientists could observe the solar system. They could not rebuild it. Again and again, every reconstruction began with the same assumption. The planets formed where we find them today. Different research teams, different computer models, different starting conditions. The same contradiction. The planets were wrong. Sometimes Mars grew far larger than the real one. Sometimes the rocky planets formed in proportions that looked nothing like the solar system we live in. The same mistake kept returning. At first, the obvious suspect was the simulations themselves. Perhaps the calculations were incomplete. Perhaps the computers simply were not powerful enough. One failed reconstruction proved nothing. The next became harder to dismiss. Then another reached the same dead end. The investigation changed. The simulations were no longer under suspicion. The solar system was... Reality kept demanding something every model had left out. The familiar solar system was no longer the answer. It had become the evidence. If the planets really formed where they orbit today, rebuilding the solar system should have been one of planetary science's simplest successes. Instead, it became one of its longest-running contradictions. Whatever was missing had changed more than a single planet. It had reshaped the entire architecture of the inner solar system. But nothing in today's orderly arrangement revealed what that missing event had been. The investigation would have to work backward. Not from theory. From the surviving scars left behind. The first scar was waiting on a planet that should never have turned out the way it did. Mars looks ordinary. It is the fourth planet from the Sun. It has seasons, polar ice, ancient river valleys carved into its surface. From a distance, it appears to belong exactly where it is. Its mass tells a different story. Mars contains only about 1/10 of Earth's mass. That fact, by itself, is not unusual. What made it extraordinary was where Mars formed. Earth and Mars emerged from neighboring regions of the young solar system. If both planets grew inside the same broad reservoir of rock and dust, they should have ended up far more alike than they are. The simulations did exactly that. Again and again, they built a Mars that was far too large. Not by a few percent. Often several times more massive than the real planet. The simplest explanation seemed reasonable. Perhaps Mars simply stopped growing early. But when researchers tested that idea, the contradiction remained. Stopping growth could not remove material that had never been missing in the first place. The models still began with too much building material beyond Earth's orbit. The investigation changed again. Mars was no longer behaving like a planet that had failed to finish growing. It behaved like a planet that had never been given enough material to begin with. That distinction changed everything. The question was no longer why Mars became so small. The question became where the missing material had gone. The strongest reconstructions pointed toward a surprising possibility. The early solar system may never have contained a smooth, continuous disk of planet-building material extending beyond Earth's orbit. Somewhere near 1 astronomical unit from the Sun, that reservoir appears to have ended abruptly. Beyond that invisible boundary, the young Mars was left to grow inside a region already stripped of much of its raw material. The evidence did not yet identify what created that boundary. It only showed that, without it, the solar system we observe today never emerged. Mars was no longer just another planet. It had become the first physical scar left by a much larger event. If Mars was the first scar, it could still have been an isolated accident. The next evidence showed it was not. It was scattered across thousands of objects orbiting between Mars and Jupiter. For generations, the asteroid belt looked like the solar system's leftovers. Fragments that never became a planet. A failed world. The closer scientists looked, the less that explanation survived. The asteroids did not belong to a single family. Those closer to the Sun were dominated by dry, rocky bodies. Farther out, darker objects carried minerals that formed in much colder conditions. It was an unexpected mixture. If the asteroid belt had formed quietly in one place, its composition should have changed gradually from one side to the other. Instead, it looked as though material from two very different regions had somehow ended up sharing the same narrow band of space. Appearance alone was not enough. The investigation moved into the laboratory. Meteorites recovered on Earth were sliced apart, cleaned to extraordinary standards, and analyzed with instruments capable of measuring tiny differences in their isotopes. The results produced something no telescope could reveal. The samples separated into two distinct families. One carried the chemical signature of the inner solar system. The other belonged to the colder outer regions beyond. There was almost nothing in between. Not a gradual transition. Not a blurred boundary. A clean division. Independent laboratories kept finding the same pattern. Different meteorites. Different isotope systems. The same separation. The investigation changed again. Mars was no longer the only clue. The asteroid belt had become a fossil record. Long before the planets settled into their modern orbits, the young solar system had been divided into two enormous reservoirs of material that remained isolated for millions of years. Something had stood between them. Whatever created that barrier was powerful enough to starve one planet of its building material, while preventing entire populations of rocky bodies from mixing across the solar system. The evidence did not yet reveal what that barrier was, only that it had once existed. And whatever had built it had reshaped far more than Mars. A barrier that powerful could not remain invisible forever. If it had divided the young solar system for millions of years, it had to obey the same laws that govern every planet still orbiting the Sun today. Gravity. The investigation had finally reached the point where observation alone was no longer enough. The next question was different. What kind of object could separate an entire planetary system without destroying it? Only one candidate was large enough. Jupiter. Today, Jupiter circles the Sun once every 12 years in a stable orbit more than 5 astronomical units away. Nothing about its present position suggests it ever influenced the region where Earth and Mars were forming. But the early solar system was nothing like the quiet place we see today. It was filled with gas hundreds of times denser than the nearly empty space between the planets now. A giant planet forming inside that disk could not simply sit still. Its gravity pulled on the surrounding gas. The gas pulled back. Those competing gravitational forces created an imbalance. Instead of remaining where it formed, a planet as massive as Jupiter was expected to drift through the disk. This was not a special property of our solar system. It emerged naturally from the physics of giant planets embedded inside young gaseous disks. The same calculations that struggled to reproduce the inner solar system agreed on something else. A giant planet surrounded by a massive gas disk should migrate. That conclusion no longer depended on Mars. It no longer depended on the asteroid belt. It followed directly from orbital dynamics. The investigation changed once again. Jupiter was no longer just the largest planet. It had become the only object capable of connecting two mysteries that had evolved independently: a missing reservoir of planetary material, and a long-lived barrier separating the inner and outer solar system. But one problem immediately appeared. If Jupiter began moving inward, why did it stop? Nothing in the migration physics suggested a natural break. A giant planet spiraling toward the sun should simply continue. If that had happened, the rocky planets might never have formed in anything like their present arrangement. Yet Earth exists. Mars survived. Jupiter is still far beyond them. Somewhere in the young solar system, the inward journey ended. The evidence now demanded an answer that orbital mechanics alone had not yet revealed. The simplest answer was the darkest one. Perhaps nothing stopped Jupiter at all. If a giant planet naturally spiraled inward through a massive gas disk, then our solar system should have ended up looking like many others astronomers have discovered. A massive planet orbiting extremely close to its star. The rocky planets scattered, or never fully assembled. That outcome was not theoretical. Across the galaxy, astronomers have found giant planets hugging their stars, completing an orbit in only a few days. Migration was no longer the surprising part. Stopping it was. The investigation changed. The question was no longer whether Jupiter could move. The question was, what could possibly force a planet larger than every other planet combined to turn around? The answer did not begin with Jupiter. It began with another planet that was still growing. Far beyond Jupiter's orbit, Saturn was forming inside the same gaseous disk. Unlike Jupiter, Saturn had not yet reached its final mass. That mattered. A lighter planet interacts with the surrounding gas differently. Under the same conditions, Saturn was expected to migrate inward even faster than Jupiter. Slowly, the distance between them began to shrink. No telescope recorded what happened next. The evidence comes from hydrodynamic simulations built from the physics of gravity and flowing gas. Again and again, the same pattern emerged. As Saturn caught up, the two giant planets became locked into a precise orbital rhythm. For every 3 orbits completed by Jupiter, Saturn completed 2. Astronomers call it a 3-to-2 mean motion resonance. The name describes the mathematics. The consequence changed the entire investigation. Once locked together, the two planets no longer carved separate gaps through the gas disk. Their gaps merged. That changed the balance of gravitational forces acting on both worlds. The gas that had been pulling Jupiter inward no longer dominated. Under the right disk conditions, the combined gravitational system began moving outward instead. Not because Jupiter fought the migration. Not because the gas disappeared overnight. The direction changed because the gravitational system itself had changed. The investigation reached its largest reversal. The force that had seemed destined to destroy the inner solar system had become the same force capable of preserving it. That did not prove this was exactly what happened. The result depended on the density, thickness, and lifetime of the young gas disk. Change those conditions enough, and the outward journey could weaken, stall, or never begin at all. That uncertainty remains part of the science. But the reconstruction solved something no earlier explanation could. It offered one physically plausible sequence capable of connecting Jupiter's migration with the surviving architecture of the inner solar system. For the first time, the investigation possessed a mechanism that could explain both destruction and survival. Only one question remained. If Jupiter really made that journey, what permanent fingerprints should still be visible today? The answer was already waiting inside the rocks. Long before anyone proposed that Jupiter might have migrated, fragments of the early solar system had been falling to Earth. For centuries, they looked like little more than unusual stones. Only recently did they become witnesses. Inside ultra-clean laboratories, researchers vaporized tiny pieces of ancient meteorites and measured the abundance of specific isotopes with extraordinary precision. These were not elements visible to the eye. They were subtle variations in atomic structure that preserve the chemical history of the environment where a rock first formed. If material had flowed freely through the young solar system, those isotopic signatures should have blended together over time. They did not. Every major dataset revealed the same unexpected result. The meteorites separated into two distinct populations. One belonged to the inner solar system. The other belonged to the outer regions beyond Jupiter's neighborhood. Between them was a remarkably clean divide. Different laboratories. Different meteorite collections. Different isotope systems. The same separation. The investigation changed again. The asteroid belt was no longer the strongest evidence that the young solar system had once been divided. The meteorites were... Unlike computer models, these measurements came directly from physical samples older than any planet's surface. They preserved a history written before Earth had even finished forming. The implication was difficult to escape. For several million years, material from the inner and outer solar system remained largely isolated from one another. Something had prevented those reservoirs from mixing. That conclusion did not identify the barrier. It only confirmed that the barrier had been real. The reconstruction was becoming increasingly difficult to dismiss. Mars required a missing reservoir of material. The asteroid belt preserved objects that originated in very different environments. Meteorites recorded a long-lived chemical separation across the young solar system. Independently, each observation raised its own question. Together, they pointed toward the same hidden history. Then the investigation widened beyond our own planetary system. When astronomers began discovering planets around other stars, one pattern appeared again and again. Giant planets were often found astonishingly close to their stars. Some completed an orbit in only a few days. They could not have formed there. The temperatures were simply too high for giant planets to assemble. The simplest explanation was that they formed farther out and migrated inward. Our solar system was no longer the only place where planetary migration made sense. It appeared to be a common outcome of planetary evolution itself. The investigation changed for the final time. Jupiter's migration was no longer standing on a single line of evidence. Laboratory measurements, planetary masses, the structure of the asteroid belt, the physics of giant planets inside gas disks, and planetary systems scattered across our galaxy. Each had begun as a separate investigation. Now they were converging on the same reconstruction. Not a proven historical route. Not the only possible explanation. but one of the strongest scientific frameworks capable of explaining why the inner solar system looks the way it does today. The familiar orbit of Jupiter returned one last time. It had not moved. Only its meaning had. What once appeared to mark the place where Jupiter had always been was now understood as something very different. The surviving endpoint of an ancient dynamical history whose exact path remains under active investigation.